let's talk about one of the most fundamental equations in all of physics and math, the heat equation. And this isn't just some abstract formula on a page, no. This is about cracking the code that nature uses to describe something as everyday as a hot cup of coffee cooling down. So that leads us to the big question, right? If you've got some object and its temperature is all over the place, how on earth can you predict what its temperature will be at any single point, at any moment in the future? It sounds impossibly complicated, but it turns out there's this incredibly powerful and elegant way to figure it all out. Okay, to get our heads around this, let's picture something. Imagine a metal rod that's been heated unevenly. Maybe it's scorching in the middle, but just warm near the ends. Then, all of a sudden, we plunge both ends into ice baths, locking their temperature down to 0. So, what happens next? How does the heat in the rest of that rod spread out and cool down? And here's the cool part. This whole physical picture, a rod, the heat, the ice, we can translate it perfectly into the language of mathematics. And this is where we get to meet the real star of the show. And there it is, the heat equation. Now, I know it might look a little intense at first glance, but let's break it down real quick. U is just the temperature. So that U sub T on the left, that's just a fancy way of asking how fast is the temperature changing over time. And the U sub X on the right, that describes the curvature of the temperature profile. So what this equation is brilliantly telling us is that the temperature changes fastest wherever the temperature graph is the most curvy. Simple as that. You know, an equation like this on its own has tons of possible solutions. To pin down the one specific solution for our metal rod, we need a little more info. We need the boundary conditions. In our case, that means knowing the ends are stuck at 0 degrees. And we need the initial condition. What was the exact temperature at every point along that rod the very instant we started this whole experiment? With those 3 pieces of the puzzle, the problem is locked in. All right, so how do we actually go about solving this thing? Well, the method it's just so clever. Instead of trying to wrestle with some complicated, messy initial temperature profile all at once, we're going to break it down into much simpler, much more elegant building blocks. This right here is the absolute core of the strategy. It comes from an idea called a Fourier series. And the mind-blowing takeaway is that any reasonable temperature profile you can think of, no matter how jagged or wild it is, can be perfectly built just by adding together a bunch of simple, clean sine waves. Let me give you an analogy that makes this super clear. Think about a musical chord you hear from a piano. It sounds rich and complex, right? But we know it's just a combination of individual pure notes. In our heat problem, that initial temperature distribution is the chord, and these simple sine waves are our fundamental notes. Our job is to figure out which notes are in that chord and how loud we need to play each one. And look, this whole sine wave strategy isn't just some hand-wavy idea. It gives us a really solid step-by-step recipe to get the exact answer every single time. So let's walk through that game plan. So here's our 5-step roadmap. First, we use a classic technique to split the problem into 2 easier ones, one for space, one for time. Second, we find the special wave shapes. These are our eigenfunctions. They can actually exist on our rod given its constraints. Third, we solve for time to see how each of those individual waves fades away. Fourth, we add all those fading waves back together. And finally, step 5, we use our starting temperature to figure out the exact volume for each wave in our final mix. So that second step mentioned this kind of scary-sounding word, eigenfunctions. But trust me, the concept is beautiful. All it means is that for a rod of a certain length, with its ends held at 0, only certain sine waves are a natural fit. They're the only shapes that work. It's just like a guitar string. It can only vibrate in very specific natural patterns. These are the natural patterns for heat on our rod. And that brings us to step 4, superposition. This is where the magic happens, where we put all the pieces back together. We take all of those natural fit sine waves, our eigenfunctions, and we just add them up. Each one gets its own coefficient, which is basically a volume knob that tells us how much of that specific note we need in our final chord. We just tweak those knobs until we've perfectly matched our starting temperature. Okay, that's enough theory for a minute. Let's see how this recipe actually plays out with a couple of quick examples. This will really show off how flexible the method is. So we're going to look at 2 cases. First, a super simple one, where the starting temperature is already a perfect sine wave, one of our eigenfunctions. Then we'll tackle something way more realistic. What if the whole rod starts at a flat, constant 100 degrees before we cool the ends? And you can see the huge difference here, right? If our starting temperature is already a pure note,
The solution is dead simple. It's just that one wave, and we watch it fade. But to create something that looks as simple as a flat 100-degree line, well, it turns out you need an infinite combination of our sine waves to build it. It's a much more complex sound than you'd think.
And this gets us to the really deep insight, the why behind it all. This method doesn't just give us a formula, it explains a fundamental property of the universe. Why does heat always smooth things out? Why does sharp temperature differences always vanish? Okay, so if you look inside the solution for every single one of our sine waves, you'll find this little piece, an exponential decay term. This is the part of the formula that tells each note how quickly to fade to silence. And buried inside that exponent is the whole secret.
And the whole secret, the absolute key to everything, is that little n squared. Now remember, n just tells us which wave we're talking about. N equals 1 is the big, gentle, fundamental wave. N equals 3, n equals 5. Those are the faster, more wiggly, high-frequency waves. And the fact that this decay rate depends on n squared, that changes everything.
This chart just shows the effect so perfectly. The main wave, our n equals 1, it fades out pretty slowly. But here's the kicker. Because of that n squared, the n equals 3 wave dies out 9 times faster. The n equals 5 wave, a whopping 25 times faster. The higher the frequency, the more wiggly the wave, the faster it just disappears. It's not even close. So, what does this all mean? Well, think about what creates sharp edges or corners in our temperature graph, like at the ends of that 100-degree rod. It's all the high-frequency, super wiggly sine waves added together. And our solution tells us that those high-frequency parts die out almost instantly. All you're left with after a split second is the smooth, gentle fundamental wave. The math isn't just giving us an answer, it's perfectly describing why heat smooths things out. And that really is the biggest takeaway. This incredible idea of breaking down complexity into simple sine waves, it's not just for heat. It is the exact same fundamental principle you'd use to analyze the sound from a guitar string, to process signals for your phone, or even to compress a digital photo. It's a universal language. So the real question is, what else can we use it to understand?